we're back to do one last problem with the women's pulse rates. And suppose I want to approach these problems in a different way. My interest is finding the pulse rate that will separate the highest 10% of women's pulse rates from the lower 90% of women's pulse rates. So we're still working on the assumption that the mean is 74 and the standard deviation is 11.3, as we have for this entire lesson. And, in this problem, instead of getting an additional pulse rate that they want to find the probability for, they've sort of presented the information to us in a different fashion. I would like to say almost the reverse fashion. They gave us a percentage, and they're looking for a pulse rate. So let me see if I can get this information in the picture, and that might help me think about it. So 10%, upper 10% would probably be about this much of the curve. I'm just guessing that would force 10% here. I don't know what pulse rate does that. I'm pretty sure it's somewhere between these two on the axis. And then, of course, if 10% of women are up there, then the remaining 90% of women would be to the left. So this is the information. Pulse rate, the bold value there, the bold text is my question mark. And of course I use the 10% and 90% to break the curve into two pieces. So I want to, again, use the standard normal model to solve this. So I have to kind of think about the standard normal model. One thing I do remember about the standard normal model is that it does give us area to the left when we use it. So when I use it backwards, because that's what we're going to do here, the information has been given to us sort of in a backwards fashion, I'm going to have to look at the area to the left, start there. So what this is, if I think about it, would be 0.90, right? Because the information that spits out of the normal, standard normal table are numbers between 0 and 1, not percent. So I'm going to convert that to 0.90. Now I'm going to go visit my table. Where's my table? And as I look at it, here's the negative side. And you start, where I'm going to actually look for answers is inside the table, not on the edges and tracing in. I'm trying to find 0.90 as close as I can get it, or 0.9000, four of them, 4 digits, out here. So if I go to 0 here, you see it's about half the curve. So I'm going to go a little bit further. And I start seeing 0.78 or 78%, jump down, 86%, 88. I'm going to start tracing over here. I notice the numbers are getting larger at this 0.1, 0.2. And I see here that we have a battle here between these two numbers, right? Somewhere between 0.8997 and 0.9015. We achieved 0.9, and this is one of the limitations of the table model, is they can't put every possible thing there. They've done the best they can here. So we have to choose one of these two to be as close as we can imagine to 0.9000. And what I'm saying here, I'm trying to get as close as possible. This is the 90, but I'm going to put 2 more zeros on it for it to feel like it's the values inside. I'm going to land on the 0.8997, believe it or not, and I am going to end up drawing, instead of tracing in on these, so I'm going to land here. That's the one I think is the closest. And I'm going to go up and trace out. So you can see it's almost the reverse action. You start in the middle of the table and you trace out to find the z-score that would trap exactly 0.9, or as close as we can get to it, to the left. So it looks like it's the z we're going to work with is z equals, let's put it together, 1.2 on the row, and the column says 8. So this is the z-score we're going to use. Let's go back and put it into where we're writing. So that's the z-score I want. So that's, that's not the answer, that's just the z-score. So let me remind you of the z. We've used this since early modules. So let's fill in what we know. We know the z is 1.28. Equals. We don't know x. That's the value we don't know. We don't know a specific pulse rate. We do know the means of these pulse rates and the standard deviation that was being given to us for the last few examples we've used with this one. So we do know those. So now what we're left with is an algebra equation. An algebra equation that we need to solve. So this one takes a little bit of algebra finesse. Let's start by cross multiplying. And if you want to think about it, that 1.28 is understood to be over 1. Every number is, so you have some, maybe it's easier for you to cross multiply if you see it that way. So we're going to end up with the 1.28 times 11.3 and that equals the 1 times x minus 74. All right, so there we have it. No more fractions. That's the beauty of cross multiplication. So 1.28 times 11.3 is 14.464. And we have over here 1 times anything. It's just that value. The last thing we're going to do to solve for this is to add 74 to both sides. And that'll isolate our x. We'll get a nice value here. So we get what looks like 88.464. That is the pulse rate that accomplishes this feat, which is to separate the lower 90% of women's pulse rates from the upper 10%. Now we had to focus in on that lower 90% because that's the way our normal table works. But again, no longer a mystery. So I can take away my question mark. This is 88.464. And what's really comforting about that, if you look at the axis, 88.464 is a number that naturally falls between the 85.3 and the 96.6. So I'm feeling very confident about this. Hopefully my algebra is all sound down there. No arithmetic errors. But that would be R. So we could say approximately 88 beats per minute.